In the previous lesson, we gave a brief introduction about the graph and what are the kind of applications where a graph can be used. Here in this lesson, we are going to look at the basic terminology which is frequently used in graphs. So as we saw earlier, the graph is an ordered pair of a set of vertices and a set of edges. And by ordered pair, we mean that they need to be written in this order. The vertices come first and the edges come later. And both these vertices and the edges, they are sets. So V, which is the set of vertices, would be containing the list of the set of all the vertices in that graph. So if we take an example of this graph, we see that this V1 is a vertex, V2 is a vertex, similarly V3 is a vertex, and so on. So V1 to V7 over here, we see it is a set of vertices. And this depicts the cardinality of the set of vertices. That means the number of vertices that are present in the set of vertices. As we can see over here, this for this particular example is 7 because there are 7 vertices. Edges is, if we talk about an edge, then that means it is a connection between two vertices. So a connection between vertices V1 and V2, this is an edge. A connection between V2 and V7, this is an edge. Similarly, all the connections which are present or existing between two vertices, they will be coming in the set of edges. An edge is always described or represented by the two vertices it is connecting. So if we talk about this edge, but this particular edge, it is connecting vertices V7 and V6. So we can say that this is the edge that we are referring to. So E, which is the set of edges, comprises of this edge V1, V2, which is this one. It comprises of edge between vertices V1 and V3. So this one. Then V1 and V4, this one. V2 and V7, this one. V3 and V4, this one. V3 and V6, this one. V4 and V5, this one, and V6 and V7, which is this one. So we see over here that there are how many edges? 1, 2, 3, 4, 5, 6, 7, 8 number of edges. So the cardinality of the set of edges, which is the number of edges, that is 8. So the size of the graph also we can say is 8 because that is equal to the total number of edges in it. If the number of vertices, if we say that the number of vertices is n, then the maximum number of edges can be n into n minus 1 by 2. Why is this? Suppose let's see, there are 3 vertices over here. So from this vertex, there can be 2 edges at the most which are going to the other 2 vertices. So for this node, there are 2 edges. Now for this node number 2, again, there is one edge which is connecting to it to node 1 and one edge which is connecting it to vertex 3. But this edge we have already counted when we were counting the edge for node 1. So we can say that we are just considering this edge. For node 3 now, both the edges, the one that is connecting it to 1, that has also been accounted for, and the one it was connected with 2, that also has been accounted for, so 0. So the number of edges is 3 over here. That is the maximum number of edges that are possible. So if we have n nodes, so any node can be connected to n minus 1 other nodes. Okay, so if there are n nodes, so each node would be connected to the other n minus 1 nodes. However, all these edges would be accounted by twice. So we have to divide it by 2 to get the actual number. So that would be n into n minus 1 by 2. If we have 3 vertices, you can check this would be 3 into 3 minus 1, which is 2, upon 2, which is equal to 3. If there were 4 vertices, this would be equal to 4 into 3 by 2, which is 6. So you can check also. These are there would be 6 maximum possible edges. So if there are 4 nodes over here, 1, 2, 3, 4, 5 and 6. These are the maximum possible number of edges with 4 nodes. In this graph, if you see, there are only 8 edges, but the maximum number of edges that would have been possible would be, since there are 7 vertices, n is equal to 7 over here, the maximum number possible would have been 7 into 6 divided by 2, which would have been 21. 21 edges were the ones which were possible. Suppose if there had been edges like this, like this, like this, over here, here, over here, so 21 number of edges would have been possible. Right now there are only 8 edges. We can think of a graph as a dense graph. A dense graph is a graph which has too many edges, and that by too many we mean that the number of edges are close to the maximum number of edges. So if this particular graph can have a maximum number of 21 edges, so any number of edges which are like close to 21, like say 16, 17 or 18 or 20 or 21, that would be a dense graph. There would be too many edges connecting most of the vertices with each other. So this kind of a graph if you are having, then it would have been termed as a dense graph. Okay. But if the number of edges are less, and by less we mean that they are close to the number of vertices. Here the number of vertices are 7 and the number of edges are 8. So there are very few edges in this graph. So this kind of a graph over here is referred to as a sparse graph, where the number of edges are very less. Any edge which is connecting nodes u and v. So suppose if there are two nodes u and v which are connected by an edge, then we say that nodes u and v are adjacent nodes, or they are also referred to as neighbors. Like here we can see that A and B are connected with an edge. So we say that A and B are adjacent nodes or neighbors. B and D are also adjacent nodes. B and C are also adjacent nodes. C and D are also neighbors. C and E are also neighbors. D and E are also neighbors. So any pair of nodes which is connected to each other with an edge, they are referred to as adjacent nodes or neighbors. The degree of a node is the total number of edges which contain that particular node. So if we talk about this node B or vertex B, there are two edges over here which are containing this node B. So we say that degree of node B or vertex B is 2. If we talk about the degree of node C, then there are 3 edges which are containing node C. This one and this one. So then we will say that degree of C is 3. What about degree of E? So again it is connected by this, it contained by this edge and this edge. So we say that degree of E is 2. What about node A? Node A is not contained by any edge. Its degree, we say the degree of node A is 0. It is not contained in any edge. Such a node is also known as an isolated node. When there are distinct edges which are containing the same endpoints, that means they are connecting two same vertices, a same pair of vertices, distinct edges, multiple edges, they are referred to as multiple edges. So if this is one edge over here And if suppose there was another edge over here which was connecting the same pair of vertices, then these two would have been referred to as multiple edges. Where do you think this kind of multiple edges would be required? Suppose these are two cities and we want to see how many flights are there between these two cities. And if there are two flights, so this edge would represent the first flight and this edge would represent the second flight. Suppose if there are 3 flights connecting city V4 with city V5, then there would be 5 edges which would be depicting those 5 flights between these two cities, and we are then assuming that this is the flight network which is being depicted by the graph. Self loop. An edge that has identical endpoints is referred to as a self loop. So suppose if an edge is starting from node V7 and ending at V7 itself, this will be a self loop. So any edge which is starting from a particular vertex and ending at the same vertex is referred to as a self loop. A simple graph is a graph which will have no self loop or multi-edge. So any graph which does not have a self loop or a multi-edge, like this graph over here, this is not having any multiple edges, it is not having any self loop as well. This is referred to as a simple graph. And a graph which has multiple edges or loops, that would be called a multi-graph. A path is a sequence of nodes. So if we have a sequence of nodes which begin from, say, suppose V0 and ends at Vn, then this is referred to as a path, and in this each node is adjacent to its previous node. So V0 is adjacent to V1, V1 is adjacent to V2, V2 is adjacent to V3, and so on. So if we have a path from, say, node A to D, so the path would be A, B and D. I can go from A to B and B to D. This is a path, and there are 3 vertices over here, but the number of edges are only 2. So we say that this path is of length 2. That is equal to the number of edges that we are traveling on that path. So it is a sequence of 3 nodes. A is adjacent to B and B is adjacent to D. So A to B to D, this is one path. Can we think of other paths? Yes. A, B, C, E is another path. B, D is a path. This is a path of only 2 nodes and 1 edge. B, C, D, E, this is another path. B is adjacent to C, C is adjacent to D, and D is adjacent to E. Can we say that A, C, D is a path? No, because there is no edge which is going from A to C directly. There is no edge over here which is connecting these 2 nodes. A is not adjacent to C, so we cannot say that ACD is a path. If in a path all the nodes are distinct, then we say it is a simple path. So like we say A, B, C, D. Here we are having 4 distinct nodes, 4 distinct vertices A, B, C and D. So this is a distinct path. But if we say a path like A, B, C, D, B, A, B, C, D, B, this is also a path. But here the node B is being repeated, and so this is not we cannot say that this is a simple path. A, B, C, E, this is a simple path. A, B, C, E, this is a simple path because no nodes are being repeated over here. A closed path is a path where the starting point and the end points are the same. So if we have a path like B, C, D, B, the starting point and the end point is the same. So this is a closed path and it is also referred to as a cycle. Can we have another closed path? Can you see another closed path over here? B, C, E, D, B. B, C, E, D, B. Again, the starting and the end points are the same. So this is again a cycle or a closed path. C, D, E, C. This again is a closed path or a cycle. A graph which does not have any cycle is referred to as an acyclic graph. Like we take an example over here. There is no way you can form a cycle or a closed path. So from A we can go to B, then we can go from C, but there is no way we can go back to B or back to A. So this is a graph which does not have any cycle. So this graph is referred to as an acyclic graph. A clique is a set of vertex, is a subset of the vertex set, so that every two vertices in that subset are connected with each other. So suppose if this is a graph over here, and now we take a subset of these vertices, V3, V4 and V5. If we take this set, we can see that all these vertices are connected with each other. C is connected with D and C is connected with E. D is connected with C and D is connected with E. E is connected with C and E is connected with D. So all three vertices, each pair of vertices in this particular subset, they are connected to each other. So what was the whole vertex set? The whole vertex set consisted of V1, V2, V3, V4, V5. But this is a subset of that vertex set where each pair is having an edge between it. Each pair of vertices is having an edge. Look at this another clique over here, V2, V3, V4. So V2, V3 and V4. This again is a clique. Why? Because V2 is connected with V3 and V4. V3 is also connected with V2 and V4. And V4 is also connected with V2 and V3. So all three vertices are connected with each other. That is why V2, V3, V4 is also forming a clique. What about V2, V3, V2, V3, V5 and V4? Is it forming a clique? Can we say that this is a clique? V2 is connected with V3, V2 is connected with V4, but there is no edge between V2 and V5. Since the definition of clique is that there should be an edge between each pair of vertices, that means that this particular subset is not a clique. So these were some basic terms that are used in graph terminology. We will look at more terms in our subsequent lectures.